This conference will now be recorded.
So, students, today will be learning another important topic of this chapter, mechanical properties of fluid. So, today's topic is buoyancy or the buoyancy force. Sometimes it is called buoyant force also. Then, what is the principle of Archimedes? Law of flotation. Then, equilibrium of floating bodies. And if time permits, we will take up few numerical examples. So, first of all, let me tell you one thing. Suppose there is an object is immersed partially or fully in a liquid or any fluid. When an object is immersed in a fluid, what happens? Fluid exerts a pressure that we have seen. Fluid always exerts pressure. So you can see this. There is this object, and when this object is fully immersed in water, suppose it is fully immersed, then what happens? This cubical object will experience force from all sides. You can see that it will exert pressure from all the sides, from top, from bottom, and then from both sides. But we have already learned that when an object is fully immersed, and also we have seen at the same horizontal level or same depth, the pressure or the thrust is to be the same. So the pressure from this side and pressure from this side are equal and opposite to each other. So there will be no net force or no net thrust or pressure in the horizontal direction. So that we have understood from this figure. Okay. Now let us see what is upward pressure and what is downward pressure, or if there at all any resultant force in this case, like along the vertical direction. Look here, suppose this is the, I'm just taking a line. This is the top portion or the top level of the water. Okay. From top level, you look here up to the upper surface. Suppose the depth is H1 and the pressure which this surface, the top surface of this object will be experiencing, that is due to the water column just of height this H1. And we know, if we know the, if this is water, that is fine. If otherwise also, if you know the densities, you can find out the pressure on this surface. So H1 rho G. Now you look, this is bottom surface This is the bottom surface. At this bottom surface, the pressure and also the pressure will be actually from the bottom face, to upward direction. So this will be along downward direction, and this pressure on the bottom face will be along the upward direction. That will be H2 rho G, and that is upward direction. And you can see that H2 is greater than H1. That means upward pressure will be greater than downward. That means you will have a resultant pressure I'm saying now, resultant pressure along the upward direction. So if we see the definition of pressure is actually thrust by area. So if you multiply the pressure with the area of each phase, then you get the thrust on each phase. So thrust, let us say the downward direction, thrust in the downward direction will be A into H1 rho G, and thrust on the upward direction will be same area of cross section since it is a cubic and symmetric object. So this is okay, H2 rho G. So this is the upward thrust. So you have some thrust from top to bottom or in the downward direction, and you have a greater thrust in the upward direction. So you'll have a resultant thrust in the upward direction. So there will be upward resultant thrust. That I hope you understand. Upward resultant thrust. So there will be a resultant or upward thrust on the object. So the this upward thrust experienced by this object is called the buoyant force. The phenomena involved is called buoyancy. Buoyancy, the phenomena is called buoyancy, and the force or the upward thrust which the object experience when it is immersed in a fluid or any liquid, that upward thrust is known to be the upthrust or buoyant force. Okay, buoyant force. So we have understood what is buoyancy and what is buoyant force. What is buoyancy? The phenomena in which if we immerse an object in a fluid, then the object experience an upward thrust, that is called buoyant force or buoyant force, and the phenomena involved is called the buoyancy. Madam, so far am I audible to you properly? Okay.
Yes.
Okay, I continue. So the force of buoyancy, see this buoyant force, how do you calculate the amount of the buoyant force? This amount of buoyant force can be calculated from the weight of the displaced water by the or liquid, displaced fluid by the object. The amount of the displaced liquid, because see, if you just fully immerse this object, it has certain volume. So the water of the volume of this object will be displaced. That means if you want to immerse this object, you have to have some open space of having volume this much, right? If you take a fully filled glass of water or beaker, and then you just try to drop some object in that which has a certain volume, you will see some water will be displaced. Okay, displaced from the beaker. Okay, that displaced water has certain weight, and that particular weight is the measure of buoyancy force or buoyant force. And this buoyant force or upthrust acts to this upthrust or buoyancy force buoyant force is the weight of the is equal to the weight of the displaced liquid or fluid, displaced fluid or liquid. Okay, and this buoyant force acts through the buoyant force acts through the sorry through the center of gravity of the displaced water, through the center of gravity of the displaced water. Okay, displaced water. So we'll take a few example in the like use of this buoyant force. We'll see at the last. That means this buoyant force has a lot of use in our day-to-day life and in many important sphere of life we use this buoyant force. Okay, so the center of gravity of the displaced water is called also center of buoyancy. Center of buoyancy. Center of buoyancy. Okay. All right. We'll now go to. Okay. Let me go to the next topic, that is Archimedes principle. So this is also very important to solve various problems, and after knowing this principle we'll be able to analyze many phenomenon like phenomena which we see around us. So Archimedes principle, see, it is related to the phenomenon in which we image fully or partially any object. Then what happens if you imagine object fully or partially, whether the object will float or it will sink or it will float sinking up to some level. So these are the various situations which can happen for any object if you imagine it. And what are the factors determining whether the object will be floating or sinking? Those things we'll learn from this Archimedes principle. First of all, let us know the principle. So when, like, according to this principle, when a body is partially or wholly immersed in a fluid, it experiences an upward thrust equal to the weight of the fluid displaced by the body, and its upthrust acts to the center of gravity or the center of gravity of the displaced fluid. So this is what we have already discussed a little bit. Now we'll directly go to the situation. See, this is a principle The principle states that when a body is partially or fully immersed in a fluid, it experiences an upward thrust, and that thrust is equal to the weight of the displaced fluid. And this upthrust acts through the center of gravity or center of buoyancy. Okay, that is what we have discussed. So this is the statement of the Archimedes principle. Nothing very new. Now we have to prove that the buoyant force is is measured by the weight of the displaced water. That is what we have to prove now. So suppose I have a container of water, this one. I'm just taking water, or maybe you can take any fluid which has a density rho in general. I have a cylindrical object. You can see that it has suppose it has certain height h. Okay, it has certain height h. Okay, and see the liquid has a top surface here. This is the top surface of the liquid. Okay, so from the top surface up to the top surface of this cylinder, suppose this depth is x. So h is a height of the cylinder or cylindrical object here, height of the cylindrical object. Okay, and then x is the depth of the top face of the object from the depth of the top face of the object from the top surface of the liquid, top surface. Okay, liquid or fluid. I have taken liquid here having density rho. All right, so this is the depth and this is the height of this cylindrical object. Okay, now see, as you have seen in the beginning, that this will actually experience pressure from all sides because it is fully immersed, and these two horizontal pressures or forces, they will cancel each other. Only what you will get, actually you will get two pressures which will not be able to cancel each other because the pressure exerted by the liquid at the bottom face is greater than, suppose this is now F2 greater than F1 over there. Okay, that's why it has upthrust. We have already discussed that. Now what we will do, we will try to calculate what is F1. F1 means what? A into P1. Suppose if the pressure on the top surface it is P1. Okay, so this is, suppose here P1 pressure, here is P2 pressure. So I can find out upthrust like this. So what is P1? A into H rho G. H is what? That is X, rho and G. Now F2 is A into P2. What is P2? This is H plus X into rho G. This total height into rho G. This is the pressure P2 over here. Now we can understand that there will be resultant upthrust F2 minus F1. So if we just do that, F2 minus F1, so AX, this will go off. So you will get A into AX into rho to G. Okay, this is what we will get. A into X, okay, A into X into rho into G. Okay. Oh, I'm sorry. There will be no, there will be H, not X. This will be X because if you take the difference, X will go up. So A into H rho G. Okay. So maybe I'll write it here. Here itself I'll write so that you can do it properly. F2 minus F1 is the resultant upward thrust. That is A H rho G. Another one is AX rho G. So this AX rho G and this AX rho G, AX rho G, these will getting cancelled by each other. You get AH rho G. Look, what is A? A is the area of this cylindrical object. What is H? H is the height of the cylindrical object. So area and height, that gives the volume of the cylindrical object. Okay. So volume of the cylindrical object is A into H. Okay. So you can see from here we have got resultant force, and that resultant force. Okay, let me clean everything. Oh no. So okay, so see, this is the volume of the cylinder, and if we write F2 minus F1, what we get, that is volume of the cylinder into rho into G. Okay, volume of the cylinder into rho into G. Suppose this is Vc, and V into rho means what? V is the volume of the object and rho is the density of the water. So you can see that this will give you the weight. Let me write M into liquid into G. So this is the weight of the displaced liquid. Okay, displaced liquid. So this is how we can see that the weight of the displaced liquid. Okay, all right, fine. Since it is the volume of the whole cylinder, since it is fully immersed, the volume of the water displaced will be the same as this. So this is the weight of the displaced liquid, weight of the displaced liquid, or weight of the cylinder, also the same thing here. Okay, so we can see that upward thrust. So from here we can see that upward thrust upward thrust or buoyant force. Buoyant force is the weight of the displaced fluid. Okay. All right. So we'll uh, as we go along with this concept, like Archimedes principles, we'll be solving, or we'll see now when a body is immersed in water, you look in, like in case of a practical example, like say when you draw water from well, when the bucket is inside the water, it you feel like that has a very less weight or light weight. Okay, that object is lightweight. That's what we see. That means it has loosened some of its weight. So here we'll see how apparent weight of the immersed body is. So how is the weight of the apparent body? Okay. So just a minute. So weight of or apparent weight of immersed body. So I shown as I have shown you that if you keep a body inside water, immersed here, then there will be an upthrust experienced by this object. Okay, upthrust. So we have seen that. So there is an upthrust, and there is another force that is called weight of the object. So you see when an object is immersed in fluid, let us suppose that true weight is W. Okay, the true weight. Now if that particular object is immersed in water, what happens? Its weight become apparent weight, and that apparent weight can be written as apparent weight apparent weight becomes actual weight minus buoyant force, because upthrust is there. Actual weight minus buoyant force. Buoyant force. Okay, this is the thing. So what is actual force? Actual force we have seen. Suppose W. What is the buoyant force? That is the weight of the weight of the or upward thrust. Let me write as upward thrust U. Now what is this? This is the weight of the object. Suppose this has density rho, and this is the liquid. This has density sigma. So see, weight of this will be Okay, I was just taking the opposite way. Let me just continue with that. The density of the liquid, suppose rho itself, the density of the object is sigma. Then you know, if the V is the volume, then you know, like you'll have V sigma, then you get mass time density is the volume time density is the mass into G, and this has V rho and G. Now if you take this V sigma and G common, you take common this one, you get, see, this V and G will get cancelled, so there will be rho over sigma. Okay, so this is the apparent weight of the body. So rho is the density of the liquid or fluid within which you are immersing, and sigma is the density of the body which you are immersing. Okay, so true weight W minus upthrust or buoyant force. Buoyant force is the, and now you might be thinking why these two volumes are same. Yes, these two volumes are same because when we say displace water, the water will be displaced of same volume of the immersed object. Suppose you have a very huge object, but it is immersed by a part of it, then the the displaced water will be having volume only that much, how much it is in the water, inside the water. So suppose you may have a very big object. Okay, you may have very big object, but suppose it is immersed up to here, inside the water, then the displaced water will be of volume this much only. Okay, not the whole volume of the container. So in this case, since the object is fully immersed, then W minus U, so this U is V rho and G. This is the displaced like volume of the displaced water into rho. Rho is the density of the water and G is the acceleration due to gravity. V sigma and G whole into 1 minus rho by sigma. So this is the apparent weight of any body which you immerse either fully or partially inside a water, inside liquid or fluid. Okay, now we'll learn about law of flotation. Okay, so law of flotation, this figure is very important in law of flotation. See, the law of flotation states that a body will float in a liquid if the weight of the liquid displaced by the immersed part of the body is equal to or greater than the weight of the body. I'll put this statement in a very simple manner. Suppose you have here, okay, let me not see this figure now. You have, suppose you have water only. You take two simple things. One is corkscrew. Okay, sorry, the cork. One is cork. Another one, you take a piece of, or maybe you can take a small ball made of glass. Now, if you put one by one here, you see the cork floats, but this sinks. Sinks, okay? So how it happens? This is a ball made of glass, a glass ball. This will float. Why is it so? Look, this depends on two things, whether some object will sink or float. This depends on two things. One is the weight of the object, another one is the upthrust or the buoyancy force, amount of buoyancy force. Okay, so there are two things. One is weight, true weight. Then you need to know upthrust. Okay, so these two things you need to know. So flotation states that when this weight will be exactly equal to upthrust, or this upthrust much greater than weight, then in this case what happens, and this case what happens, when the upthrust is much larger than the downward force or the weight of the object. So we'll take three situations as I was showing you. In first case, look, the upward thrust is less than the weight of the body. So since the weight of the body is more, that means the weight is always acting downward. Okay. So the body will be actually fully immersed, and so we'll take a few conditions that when the downward pull or the weight of the body is greater than the upthrust, then the net force is in the downward direction, and that's how the body will sink in a liquid if its density is greater than. So from here what we can write, if this case, first case, W is greater than U. Okay, so if, so we know this is V sigma into G, this is V into rho into, I'm sorry, just a minute, V sigma G and V rho G, sorry. And in this case, you look, the sigma has to be greater than rho. Sigma is the density of the object. Density of object. Density of the object. And this is the density of the fluid or liquid. So when the density of the object which is immersed in certain fluid is much greater than the density of the fluid, then the object will surely sink inside the fluid. So that's why you look here, it is totally sink, and in this case sigma is greater than rho. Okay, that is the condition for sinking. Now what is happening, we'll take another situation where both are equal, like upward thrust and the weight of the body. If they are both equal, if they are both equal, look this situation, then what happens, there will be no net force. That's why that will be actually floating, floating, but it will be immersed fully within the water and then floating. Okay, so it will float with uh, it will float fully immersing in water. Now we'll see another case where the water has much greater density than, or the liquid or the fluid has much greater density than the object. So in that case, the upward thrust will be much more than the density of the object. So this is the law of flotation. So there are three situations we have discussed. So I'll just repeat what all things happen when W greater than U, that is the first figure. A body sinks in a liquid if its density is greater than the density of the liquid. Okay, so when the upthrust and weight both are equal, a drop of olive oil we must have seen, like in the mixture of equal amount of water and alcohol, make a olive oil drop float on the water surface or the mixed surface of the mixture, and the gravitational force W is less than the upward force, then the body will emerge in water. This is because the body sinks only due to its weight. Okay, so here see, in this case sigma, that means the density of this object is greater than the rho. In this case rho may be equal to sigma, and here again sigma is less than rho. So in this case, as you see, this is W is equal to U, this is W is less than U, and this is W is greater than U. So these are the condition. When actually these two are equal, then the object will be fully immersed, and then it will be fully immersed, but it will float. It will not sink, it will float, but the whole object will be inside the water or liquid. So this is about law of flotation. Now we'll see few examples of this floating. Suppose the ship, big ship is actually made of steel, so it has density much greater than sea water or simple water. But since it has a greater volume, see, look, this is the volume is synced. It has a very great volume, and the water is it displaced has greater water displaced by this ship will be greater, much greater than the weight of the whole ship itself. Okay, so this is how the ship is floating in the sea water. This is floating of cork. We have already discussed. Okay, so this is another way of floating in water. Suppose there is a tube, hollow tube. You can fill the water in that. So we see this has only air inside it. So it has very less weight. This tube has very less weight, but the volume is much greater. This is so this has very light weight, but it has huge volume. So it can displace water of a great volume. Okay. So that's why, on the other hand, our body is having actually much greater density than sea water or any water, normal water. So if we try to float, we will not be able to float. We will sink actually because of this. We have greater density. But when we take use of this kind of object, which has very less weight but he had huge volume, then it can displace a water greater than the human body itself. Okay, so it will displace a water which will be having much greater weight than the human body. So that's how human being or any person can float with the help of this tube. Okay, so we have completed this flotation, law of flotation. Now we'll see equilibrium of flotation. So in equilibrium of flotation, you have to remember few things. One is that any object, it has some weight, so it has a center of gravity. Center of gravity. Center of gravity and center of buoyancy. Okay. Center of gravity and center of buoyancy. So suppose you have certain object in the shape of something like this. So this object while floating will be floating if the center of gravity and center of displace of water, these two becomes equal. Okay, so center of gravity, let us say G, and center of buoyancy H. So this GH, when they come in the same line, there is a possibility that there will be cancellation of this Okay, so what I was trying to say, this G is center of gravity, suppose, and this is center of buoyancy. When they come in same line, then the object or floating object is said to be in stable equilibrium condition. But suppose it has its center of gravity, center of, this is center of buoyancy and this is center of gravity. Originally it would have been there, but if suppose somehow they are displaced from each other for a certain object, like here, then it will experience a torque. Actually, it will experience a torque and it will try to rotate about that torque. Okay, so there will be translational equilibrium, but there will be no rotational equilibrium. Okay, so this is equilibrium of flotation. So equilibrium of flotation is seen in two, like just by understanding few things, like when your center of gravity and center of buoyancy are in the same line, then that object is actually will be that object will float, and their situation will be or their existence will be stable. Okay, that is called stable equilibrium also. And if you displace an object from stable equilibrium, it will not be disturbed very easily. And in case of unstable equilibrium, the center of gravity becomes center of gravity and center of buoyancy. They will not be in the same line. First of all, center of gravity, suppose, and center of buoyancy. So if they are not in the same line, then they will not be in the stable equilibrium, and there will be a torque acting which will try to rotate the object. Okay, so this is about equilibrium of floating of bodies. I think I'll stop it here for today, and we'll take up numerical example on this new Archimedes law and etc. in the next class, where we'll solve few problems in great detail from NEET and JEE paper. Okay. Okay, bye for today.